Good morning, friends. Today we'll talk about algorithm analysis. So, before going for the analysis of algorithm, first we will go for algorithm. What is an algorithm? So, all of you know, algorithm is set of instructions that we write in order to solve a particular problem. Okay, an algorithm is a finite set of instructions which is followed, accomplish particular task, or it's a sequential step of instructions of the program. Transforms an input into an output. So we'll get for a particular input, we will get a particular output from the algorithm. Okay, so these are the properties of an algorithm. We have five properties for algorithm. Every algorithm should have an input. There are zero or more quantities which are externally supplied. Input should be there. You can write algorithm without that. That's why it's written as zero or more. Output, at least one quantity is produced. Every algorithm should produce a particular output. Then next property is definiteness. Each instruction must be clear and easy to understand. Everything must be clear. What we are writing in the algorithm, should be clear. Another important thing is finiteness. Algorithm will terminate after a finite number of steps. So we don't want an algorithm which is infinitely going. We want a finite algorithm. So finiteness is another important characteristics of an algorithm. Effectiveness. Every instruction must be roughly worked out using pencil and paper. So all the things should be clear, more effectively generated. Okay, so these are the five properties of an algorithm. Okay. So why we studying algorithm? Why study of algorithm is important? What is the importance of algorithm? Algorithm help us to understand scalability. So we will understand the problem better if you write the algorithm. Performance often draws the line between what is feasible and what is impossible. That's a very important statement because before writing a program, we will understand that whether the design, the solution exists or not, if it is solvable or not. By writing the algorithm, we will understand that. Another important algorithm, mathematics provides a language for talking about program behavior. So everything is clear after writing an algorithm because we will have we can have mathematical notations. Using that, we uh, can create an we can think about the solution. What it will be providing, all that things it will be clear by writing the algorithm. So writing an algorithm or studying algorithm is very much important because we will have a clear output or clear view about the solution. What we have a problem, we write the algorithm. After writing the algorithm itself, we are clear what is the expected outcome when we after implementation. Algorithm analysis. So this is topic that we are going to study. How to analyze a problem. So we can, I told you, for the same problem we can have different type of algorithms. So which is better? Which is the best algorithm? How we will decide that? For that we want to analyze the algorithm. Okay, but this is a technique to measure the performance of the algorithm. So using this technique, we are going to measure how well the algorithm is working. It provides user friendliness, maintainability, and usage space that determine the quality of algorithms. So a lot of things it will be checking. Based on that, we will say, okay, this algorithm is the best or the good algorithm compared to the other. Efficiency of algorithm can be analysis at two different stages, before implementation and after implementation. Normally, we will not think about before implementation. We will be writing algorithm. So normally when we think about analysis, we simply thought, okay, we will write the algorithm, we will implement the code, and based on the code, we will decide whether the algorithm is good or bad. But it will take a long time to implement. We have written a large algorithm, and to implement that algorithm into a program, it will take a long time. After implementation, we will find out that okay, this algorithm is not suitable. It's not that good method. So there is methods to analyze the algorithm before implementation also. Okay, so there are two stages are there. One is before implementation and one is after implementation. Okay, algorithm analysis deals with execution running time of various operations involved in it. That's the main thing. Okay, what analysis does? It deals with the execution running time of various operations. What is the time taken for each operations? That is the algorithm analysis. Running time of an operation can be defined as a number of computer instruction executed per operation. That is another. What is running time? Running time simply means how much time it will take. It will take means how much time the computer will take to process that. So that's the analysis method that we are going to use. Okay. So next, there are two type of algorithm analysis are there. Then priori analysis and posteriori analysis. Okay, in priori analysis, this is a theoretical analysis of algorithm before implementation. It's a theoretical approach. Efficiency of algorithm is measured by the speed, how fast is it executing. For that, we have some constraints are there. Using that, we will calculate. That is, priori analysis is done before the implementation. Constants have no effect on implementation. On this case, constants are not calculated or not considered. Okay. Then posteriori analysis. The selected algorithm implemented using programming language. This is executed on a target computer machine. In this analysis, actual stats like running time and space calculated after implementation. So all that things is this is a posterior method where we will be implementing that, and based on that, we will decide which the algorithm analysis. Okay. These are for calculating the complexity of algorithm, we will consider two main components. One is time complexity. Time complexity. This is a function describing the amount of time an algorithm take in terms of amount of input to the algorithm. How much time it will take? How much time we have a problem, because depending on the input, the time may vary. So for a fixed input, what is the time taken? So like that we use for analysis, that's the time complexity. Our time complexity calculates the time taken for execution based on the input. Okay, time complexity we will take normally in posterior approach. We will consider time complexity is a combination of compile time plus runtime execution. That is the time taken, time complexity. Okay, next one is space complexity. Space complexity of an algorithm represents the amount of memory space required by the algorithm in its life cycle. Okay, not as a program. When it is running, what's the memory space required? Because two types of space are required normally. One is fixed part and variable. Variable part is also there. Fixed part means required to store certain data and variables that are independent size of the problem. For example, constants. We are declaring a constant. Program size. We have written a program. There will be a fixed size for the program. So all these are fixed parts of the program. So that's also a condition for space complexity. Another thing is variable part. It required by variable whose size depends on the size of the problem. So it's a for example, dynamic memory allocation. Okay, an array has been dynamically created according to the user requirements. We are being creating that. So that's the space complexity. So these two are the two conditions that we use when we analyze an algorithm, complexity of the algorithm, even in before implementation and in after implementation. Before implementation, we will consider the time complexity and space complexity by checking at the systems. Okay, so we'll have comparison of priori testing and posteriori testing. Priori testing, we will use the algorithms. We don't have the programs. Posteriori, we will have the program. Priori testing, independent of the language. It's not, we are not writing any language there. It's a language dependent. When you are using C program, it will be different. Java program, it will be different. Okay. Hardware independent. It's not depending on any hardware. It's hardware dependent posteriori. Third, time and space functions are calculated. Here we will have a function. Again, we will be using time and space, but we don't have an actual value for that. So we will generate a function for using this priority testing. Okay, this is the estimate function. Posterior methods, we will have a time. We can have this time and how much bytes it is been using. So all that things we can calculate. Okay, another one, the RAM model. Okay, normally we prefer priority testing because the advantage is in priority testing is that before implementation itself we can estimate the time. So even though there are so many constraints are there, we will not get the actual time, but we will have a feel of it. Okay, we can have a feel so that priority testing is normally done. For priority testing, one model is called the RAM model. Okay, it's a machine-independent algorithm design depends on hypothetical computer called random access machine. Okay, it's a RAM. So we will make certain assumptions when we are using this RAM. First assumption is each simple operations, this plus, minus, if, etc., take exactly one time. Even for multiplication, it will take the same time. It's saying that for addition and multiplication, it will take the same time. Okay. It is not considering multiplication will take more operations. It is not considering anything like that. So it's saying that all the simple operations will take only one time. Assume it as one time. Second condition is saying that loops and subroutines are not considered simple operations. Loops and functions are not simple operations. Instead, they are composition of many single step operations. So if you write a loop, if I am writing a for loop, that will not be considered as a single statement because that is being repeatedly executing. So each step will be considered as a composite statement. That's another assumption. Then each memory access take exactly one time. That's the third assumption. So assuming that even you already know that. Suppose I have a data in my hard disk. If the CPU want to take the data, it should be moved to the RAM, then to the cache, and finally to the CPU. The time will be more. But in this RAM model, we are assuming that all that will take only one time. So we are neglecting so many things in this RAM. So advantage is that we can get a feel of how much time it will take. It is not the actual time. For actual time, we have to calculate the machine. We have to run the machine and we have to do the real things. But main problem in that is we have to implement we want to convert that algorithm to a program. So we are taking certain assumptions. These are the main three assumptions. First assumption is all the operations, all the simple operations, even though addition and subtraction will take different time, it is assumed as one, same time. Second one, loops will be considered as composite simple statements. Third condition, memory access time take exactly one time. This is a RAM model. Okay, under RAM model, we measure the runtime of an algorithm by counting up the number of steps it takes on a given problem instance. Okay, so RAM model is saying it will count the number of steps execution. So that will be used as the running time. Time will be calculated based on the number of steps it is being executed. Okay, it's called the frequency count. This number of steps is called frequency count. Frequency count is a count denoting the number of time of execution of a statement. How many times a statement is being executed? That is called the frequency count. That is the main criteria of this RAM. Okay. By assuming that our RAM executes a given number of steps per second, the operation count converts easily to the actual runtime. We are assuming that the RAM will process each statement completely. Each statement will be processed in one time. Okay. RAM is a simple model of how computer performs. The common complaint is that It is too simple that these assumptions make the conclusion analysis too coarse to believe in practice. So it's not the practical. We don't want the actual time. We just want the estimate. So this RAM model is heavily used. Okay, so these are the main problems I already said. For example, multiplying two numbers takes more time than adding two numbers on most processors, which violate the first assumption of the model. First assumption is saying that addition and subtraction will take or multiplication will take the same time. Memory access time differs greatly on whether data sits in the cache or in the disk. Another thing, the third assumption is violating the third assumptions. Despite these compliance, RAM is an excellent model for understanding how an algorithm will perform on real computer. Okay. It strikes a fine balance by capturing the essential behavior of the computer while being simple to work with. So it's still used because we just want an estimate. We don't want the actual value. Okay, now we will study about how to analyze, how to count this frequency count, and how to estimate the time. Okay, let's take an example. I have a for loop for I equal to 0, I is less than n, I plus plus. So we will estimate each points. I equal to 0. How many times it will be executing? Only one. Okay. I is less than n. How many times it will be executing? It will estimate n plus 1 times. I plus plus. It will estimate to, it will execute n times. STMT, this is statement, n times. So totally, this will take 1 time, this will take n plus 1 time, this will take again n time, this will take n time. Okay. So we will sum it up together. Then this will be 1 plus n plus 1 plus, there is n plus 2, n plus 2. Here is n, 3n. 3n is there, 3n plus 2. That's a value we are getting. We will neglect the constant values. 3n plus 2. 2 is a constant, 3 is a constant. We will take only n. So we say that the complexity or the time value is n. Okay, so that is this n. So in this posterior approach, I told you, we'll write it as a function. Not the real value, we will not get the real values, only we will have a function. So we are saying that this time complexity of this algorithm is n. Means we are approximating, we are neglecting the constants, and we are saying, okay, this is the maximum, this is the n time. Now what is this big O? This is simple, we will learn later. So for time complexity, we will write like this. It is called as big O. Big O of n. So it's stated like this. The complexity of this algorithm is f equal to big O of n. That's the complexity of the algorithm. So we will study about these symbols later. First, we will just try to learn how to calculate this. Calculation is very simple. Each statement will be counted, and we can sum it up, and we will take the largest value. Okay, here 3n plus 2. So we are approximating it as n. We are not taking the constant values. Constant values are neglected, so the value will be f equal to n. Okay, we'll take another example. I equal to 0, I is less than n, I equal to I plus 2 statements. So here what is going is that initially I equal to 0 is there. Statement, this will be executing one time. This one we want to identify because it has been incrementing by 2, not by 1. If it is 1, then we can say it is n plus 1, and this is n, this is n, the same problem. But here the value has been changing by I plus 2. So initially it will be 0, then it will be 4, then it will be 2, then it will be 4, then it will be 6, then it will be 8, like that. It will be going like that until we reach a point when I value is greater than n. Okay. So we'll make an assumption. K, at point K, when I equal to K, surely it is not I is less than n. Before normal operation, it will not execute n times. it will be surely less than n. Okay. The value, because it has been incrementing by 1. So the value will be always greater than, always less than n. It is not n plus 1. It is always less than. But I told you we will neglect the, suppose n is always, okay, I am taking k, and k is I equal to k, I is greater than n. Condition is satisfied. So up to k I goes. K is surely less than n. But I told you we will be neglecting the constants. So n minus 1, n plus 1, all that things will be taken as n itself. So the complexity will become again n. So we are making an estimation. It's not the actual time. Because I'm sure that the complexity of both algorithm, both statement is not n. But I am making an assumption. Okay, it can be approximated to n. I am assuming. Okay, so it's surely less than n. Okay, we'll take another example. So for I equal to 0, I is less than n, I plus plus. J equal to 0, J is less than n, J plus plus. And statement is there. This is within double for loop is there. Okay, we'll take this example. This will execute one time. This will be n plus 1 time. This will be again n time. Here, this statement will execute n time. Okay, this statement will be executing n time. This is n time. This one, n into n. N square time it will be executing. This will be n square plus 1 time executing. So totally n square, some n square values we will get. This will be n square. This will be n square. Okay, 2n square will be coming there. This is also n square value. So 3n square will be there. 3n square plus n will be there. How many n's? 2n will be there. 3n square plus 2n. Here is also n. So 3n plus 2. Some value we will get. But we will neglect all the constant and we will take the largest value. So largest value is n square. So it is f equal to order of n square. Okay. So we will take another example. For I equal to 0, I is less than n, I plus plus. J equal to 0, J is less than I, J plus plus. It's within statements. Just evaluate. Okay. This will take one time. This will take n plus 1 and this will be n. Okay. I am taking n plus 1 and I can consider it as n itself. Okay. N, all n. What about this statement? Okay. Initially j equal to 0. J is less than I. If I is 0, then it will not execute. If I is 1, it will execute one time. Okay. If I is 2, it will execute 2 times. If I is 3, it will execute 3 times. If I is 4, it will execute 4 times. If I is n, it will execute n times. That's the thing. Sure. That means this statement, this inner loop will execute. This will be n, and this inner loop will be executing not n square times, not like that. This will be executing. Initially it will be 0, then it will be 1, then it will be 2, then it will be 3, it will be 4, like that up to n. That is, it will be 0 plus 1 plus 2 plus etc. up to n. That much time this inner loop will be executed. Okay, that is n into n plus 1 by 2. That is n square by n square plus n by 2. N square plus n by 2. That is again order of n square. Largest value is order of n square. So we will get the complexity as order of n square. So another statement. I equal to 1. I is less than n. I equal to I into 2. Okay. I into 2. And statement is there. Okay. I has been incrementing 2 times. So initially I will be 1. Next time it will be 2. Next time it will be 4. That is 2 into 2. Next time it will be 2 into 2 into 2. It's 4 into 2, 8. That is 2 into 2 into 2, 4. Next time it will be 2 into 2 into 2 into 2. Like that. So at the kth position, we are assuming it as k. When k, suppose I equal to k, I is greater than n. Then kth position it will be 2 raised to k. So it will be 2 raised to k. So assume I is greater than n, then I equal to 2 raised to k. That is 2 raised to k. 2 raised to k, this is greater than n. And we will find out the k. K is, apply log 2, log n. So k is log n. Log n value will be there. So this is the complexity of this one, order of log n. Okay, next one. I equal to n, I is greater than 1, I equal to I by 2. A statement is here. So here I is been dividing by 2. So initially it will be n, then it will be n by 2, n by 2 raised to 4, n by 2 raised to 3. Like that we will assume it as k, up to k. That is n by 2 raised to k. That is I equal to n by 2 raised to k is less than 1. This condition will break. That is n is equal to 2 raised to k. That is we will apply the log. It will be k log. K equal to log. Again it will be log. This part will be also. Okay. Another example. I equal to 0. I into I is less than n. I plus plus. Okay. The statement is there. I into I. Initially I is 0. Then it will be 0. I into I is again 0. It's I. Okay. 1. Then 1 itself. 2. Then 4. 3. It will be 9. K. It will be k into k. K into k. There is k. K square will be there. There is I is equal to k square. K square is greater than n. There is k is equal to root n. So we will get the root value as k. So we will go through different examples more. We will train this more. So this is the thing. So only thing is frequency count is a factor in this approach, RAM model, where we will count the number of statements and we will assume that each statement executes only one time. Each statement is considered as a single count. That's a main assumption. But what we are saying is that we don't want the actual value. We just want to estimate, and we want to make a decision whether which algorithm should be used for implementation. So that's it.